Yes. Right. I was hoping you would
Entonces yo le dije, hay que utilizar el Q&A con los profesores.
Pues Carlos, yo creo que se pueden, entonces, sentar. Bueno, sí.
Sí, va a ser Marius, que está por aquí. Y
Ya le va a mandar los
mandé el short letter. Y el otro queda todavía por una ronda interna y después ya tengo todo el feedback de interno. How are you, man? Good, how are you? You've earned
Okay.
a bottle of water.
You got my. No need. Seriously. No, please.
just in case.
Do you have one?
Yeah, I do. I can have 6 seconds. 7.
So.
Yes.
Okay.
Okay.
Is the arrow?
Yeah.
Yeah. Okay. Good. ¿Dónde estás sentado? ¿Estás sentado allá? Okay, bueno. Muy bien, tu viaje.
Muy bien, sí. We have very nice places around within the.
Is that on the
No, both.
Both. Okay. Yeah, I was gonna say the silicon.
Yeah.
How many system was your the first question. I was hoping that was. I was hoping these were polysilicon shipments coming out.
A lot of cold. Yeah.
Should be $5.
Yeah, he has a we were 11 different.
We are sitting.
committee Q&A, and then you leave in the committee discussion. So all of that has to be over. So if you dial back, it's probably 5 minutes of committee discussion, 10 minutes before that, our Q&A, and then 15 minutes after the audience Q&A. So we're looking at are you assuming you have
That's not yes.
I
I'm not sure. I shared with family and some friends, so
Good. Yeah.
some of them are in there.
Hi, nice to meet you. Let's see.
We'll give it a few minutes for the remaining committee member to show up.
No, gracias. Yeah. Take a run and find for another. Morning. How are you?
Good morning, nice to meet you.
Oh, yeah.
Nice to see you.
Hello, yeah.
I only heard you on the phone.
Yeah, that's right. Face to face. Okay. Sorry.
Okay, ladies and gentlemen, we're here assembled today for the thesis defense of Sergio Castellanos, who's been a member of our PD lab. We have the delightful presence of the committee as well, Professor David Parks, Professor Carlos Canizo, who's joining us from IES Madrid, and Professor Sarah Williams as well. We have in the audience Dr. Marius Peters and Professor Ali Sachs as additional members to fulfill the quorum. And of course, ladies and gentlemen, you yourselves, colleagues, friends, and family, and we welcome you all. Sergio comes from a country, the country of Mexico. There were over 150 gigawatts of solar installed worldwide as of last year, and in Mexico, only 80 megawatts of solar. This represents an enormous opportunity for the country of Mexico, about 150 million people, solar base that on average is larger than the United States for area normalized. And Sergio's been doing work in an area that has some good potential impact in industry, in crystalline silicon PV, which accounts for over 90% of the world market. And I think not only from a technical point of view, but also from a personal point of view, represents really the triumph of the human spirit in so many ways. So it's a great pleasure of mine to introduce Sergio Castellanos, a person who has demonstrated some very nice results, but also represents, in a way, solar's future and the potential that is to come. So Sergio, please.
Thank you very much, Tony, for that kind introduction. Good morning, everyone. Well, by now you know I'm Sergio Castellanos, and today I'm really happy to be sharing with you a portion of the work that I did all these years at MIT. And the work is entitled The Electrical Impact Assessment of Dislocations in Silicon Solar Cells. So when we think about the solar potential, it's huge. We see in here a visual representation from the energy human consumption in a year. It's about 15 terawatt years. When we bring solar into the picture, you can see the potential is huge. This represents the amount of availability from solar energy. And when you compare this versus other renewable energy, such as wind, biomass, geothermal, and so on, solar is by far the biggest. It's been said that if we're able to capture efficiently incoming solar radiation, we would be able to suffice the entire energy needs for a year just by capturing 1 hour of the solar radiation. We can do that in twofold. One, solar thermal converts solar radiation to heat and then to work, or solar to electricity, and that is the photovoltaic effect, the one I work. Specifically, in PV, I work in silicon solar base cells. So why silicon? First of all, it's the second most abundant material in the Earth's crust, but it has also gained a lot of knowledge transfer from the integrated circuit industry. Because of these two variables, as Tonio mentioned, PV now comprises about 90% of the entire PV population. This is silicon-based. Of the entire PV population, 90% of them are silicon-based. And these are really, really exciting times. As you can see on the x-axis, this is the PV module shipment, which scales with deployment of PV. It's increasing and increasing. And on the y-axis, you see the module price, which has been dropped. This has been as a function of different years, so as a progression of years, module price has been declining. And this is a side effect of the technology innovations that have occurred. These innovations have been aimed specifically at increasing efficiency. However, there are some obstacles for efficiency. In my research, I studied dislocations, which is a defect that reduces efficiency. Today, I'll walk you through some of this defect, and I'll give you an introduction about how it impacts efficiency, and then I'll start with the contribution of my PhD thesis. A small portion is focused on reducing dislocation density, and the rest is some characterizing dislocation in two different materials, and then I'll end up with another spatial characterization method that I'll talk about. So let's start with how dislocations impact efficiency. Whenever we think about PV, the things that come to mind are efficiency and cost. You here see on the x-axis different technical drivers, and on the y-axis you see the module price sensitivity. It's evident from here that efficiency, that is, any change you perform in efficiency, will have the highest impact on module price. So it's a big concern for us and one we strive to increase constantly. We also see in this graph silicon wafer. From here, that is the material that you create solar cells from, in this case. And we are aiming to have not only high efficiency, but from here, any change in the silicon wafer that you have will produce an impact on the sensitivity of price. So we're aiming to have low material cost, but that material have high efficiency. Now, where does this all efficiency and cost fit into the picture when you create a solar cell? Well, let me walk you through the process of creating a solar cell. So you start first by a mixture of different gases, just as you would in a refinery in a petrochemistry. You distill those gases by mass. You condense them into these polysilicon rods. You break them into chunks of silicon, and this is for the ingot-based multicrystalline silicon and other variables of it. But it's ingot-based system. So you load the different silicon chunks into a crucible. You melt it. Following the melt of the feedstock, you solidify. You crop bricks out of the material. You saw them into wafers, and then those wafers is the final product you have in here. At this point, you have lost about 50% of the material. So whatever you have left, it has to be real good. After that, that's a bare wafer. You need to still process even more to get a final solar cell. You apply a texturization process, which is changing the surface morphology such that you have more internal reflection of light. You do a phosphorus diffusion gathering, this is for P-type. It's a process that creates the p-n junction, which is required for a solar cell, but it also extracts the impurity out of the material. You apply a silicon nitride coating, which is anti-reflective coating, absorbs more light. And finally, you do some metallization process to extract the carriers out of the sample. It's in here where most of the defects nucleate, and particularly the ones I will talk about, which is dislocation. What is a dislocation? For those of you who are not very familiar with this, a dislocation can be represented as follows. You have the perfect cubic structure, in this case, elucidated with these spheres corresponding to atoms. You have an ordered array of atoms, that is your crystal lattice, and within that, if you insert half plane, you're distorting the lattice. That is, you are creating a dislocation. If you look at an isometric view of it, a dislocation will start at a surface, but it also ends at a surface. From now on, I'm going to talk about dislocations by mentioning that this is the schematic representation of dislocation. That is an inverse T shape. And this is, for those of you who know more about it, this is an edge-type dislocation. So dislocations come in the crystallization process as follows. What I'm showing you right now is a cross-sectional view of a crucible with the solidified silicon in it. Dislocations come because you are exceeding the local yield point of the material. Essentially, if you see a dislocation, that means that the plasticity regime is kicking in. So this is a representation of the different thermal fluctuations you see upon solidification. And so if we extract a slice, that is a wafer, out of this material, apply some chemical treatments to reveal the defects, this is what we end up seeing. This is an optical micrograph taken with a microscope, top view. All these contours correspond to grain boundaries, which is the crystallographic defect, and all the dark spots correspond to dislocations revealed as edge pits. I told you dislocations are bad. Well, they come about as follows. Dislocations are represented again as an inverse T shape, have a core, but they create a stress field surrounding the vicinity of the core. So that stress field creates an influx of impurities to its core. It can supersaturate and precipitate, but it also drives a cloud around the dislocation. Again, if we took an isometric view, we see a dislocation starting at a surface, ending at another surface, and going through it. You see some precipitates inside the core, but also the cloud of impurities surrounding. Why is this bad? Why having impurities around this location is a bad thing? This is clear when we see this image. On the x-axis, you see the metal impurity concentration. So you start increasing the metal concentration. The y-axis denotes the efficiency. You decrease the efficiency. That is for a different set of metals. In this case, what you're seeing is transitional metal. So metals are really bad, and the combination of these two makes it even worse. If you want to represent this schematically differently, you have the photon, the incoming photon, creating an exciton, that is an electron-hole pair. The carrier will travel a distance before it reaches this location. There is a Coulombic attraction in there that distorts the band gap, and the introduction of a metal impurity in there creates an energy level within the band gap. Now this reduces the energy barrier, and then the electron recombines with the hole. Physically, this will be called the lifetime. That is the time the carrier takes before it recombines. You can relate diffusion length. Diffusion length can be related to lifetime. Lifetime would be the time that it takes before that happens, with every combination. And this, experimentally, we use it very consistently to correlate with efficiency. So, as you can imagine, a lifetime from a state that has many metal impurities within the energy level will be much lower than a lifetime that you would get from a very clean material. And so in this case, on the x-axis, you have lifetime, and the y-axis, you have efficiency. So we strive to have long diffusion lengths, which are, in a way, long lifetime, high lifetimes, to have higher efficiency. And this is true for different cell architectures that you would find in the market. We want lower defect density. We want to improve the lifetime such that we can achieve higher cell efficiency. So that brings me to the first contribution of my PhD work. I talked about how dislocations are bad, and the first logical question is, okay, can we reduce them? So there's two mechanisms for reduction. One is pairwise annihilation, that is two dislocations from different sides encountering each other and thus restoring the crystal lattice. So you see here the half planes meet, create a full plane. The lattice is again restored. You can represent it here inside a grain. This is the grain boundaries, these locations facing each other, and thus annihilate. The other mechanism is that they would sink at a free surface, that's shown in here. This location would move out either to a grain boundary or to the edge of the sample, and thus, again, the lattice will be restored. Now, this rate of reduction has been governed, has been modeled before, and it's a function of different properties, mainly material properties. But one variable that governs this equation is temperature. So what is the relation between temperature and this location? Well, if we think about this location at a temperature below the brittle to ductile transitions, that is from being brittle, that will fracture to brittle to ductile, that it will plastically deform. This is 500 to 600 Celsius. Anything below, these locations are immobile. Start increasing the temperature a bit more, and you will see that now that these locations can move along preferential planes. That is, they start to glide. Furthermore, you turn the knob higher, temperature rises, and now these locations can not only move along glide planes, but they can also climb out of their planes. So with this, you increase the probability of these locations finding each other from opposite sides or sitting at a free surface. So with this, the hypothesis is that annealing will enable dislocation motion, increase the probability of dislocation reduction at the same time in silicon materials. To test this hypothesis, I designed a time temperature profile very similar to what's found in literature and similar to the work that has been done in a group. In this case, though, I extended the duration of this time temperature profile for a full day. And you can see here the temperature is pretty high. It's 1390 Celsius, close to the melting temperature of silicon, which is 1440. Then it's followed by a slow cool down, just so we avoid those thermal fluctuations that I told you about, and you end up with a hopefully dislocation density reduction, which is the case. We achieved a 45% dislocation density reduction. This was consistent in a way with previous reported values, but my contribution was expanding into looking into this and expand the knowledge. The reason is, in this reduction, we saw that the reduction was not a homogeneous. So to understand why was this not a homogeneous reduction, I performed a set of characterization techniques to understand the root causes. And that is my contribution. When I say it's not homogeneous, this is what we see. We see a region with two different dislocation edge pit clusters. This is before annealing, and this is after annealing. You will see two arrows, one pointing to a dislocation cluster that was reduced after annealing, and one that it did not reduce after annealing. So we're seeing this inhomogeneity. So this is limiting already the efficacy of this technique. To understand, again, the root cause, which was my contribution, I applied different techniques that I'll talk about. First, I selected a region of interest with two dislocation edge pit clusters. This is an after annealing image of the optical microscope. We see again that there's two clusters. I highlight them. Interestingly, one of them is at a grain boundary. So the first question was, okay, is this a function that the grain boundary is creating stress such that it's nucleating dislocations? But if that is the case, why are we not seeing a grain boundary here? Well, to quantify where the grain boundaries were dispersed or were located, I performed a grain orientation analysis through EPSD backscatter diffraction, electron backscatter diffraction. And whatever change in color you see denotes that there is a grain boundary in that location. Indeed, for one of the clusters, we see that there's a grain boundary, but not for the other one. So this is to think that there's something within the bulk. I applied then a different technique, which is infrared transmission. I'm seeing now through the bulk. I'm using a wavelength of 1100 nanometers to see through the bulk, and I see different things. Interestingly, inside the ellipses, I'm seeing spots that are absorbing light or diffracting light. So I'm not sure if it's a surface. I wasn't sure if it was a surface or something within the bulk absorbing. Now, something within the bulk would be another material that would be creating stress. So within that, I applied a stress imaging analysis done through the infrared birefringence imaging. So what you see here, yellow is high stress, white is low stress. All the dark spots that are outside this region basically disappear. They don't impart any stress, meaning that it could be a surface effect of the polishing of the sample. However, whatever is inside is causing internal stress in the bulk of the sample. That is the potential reason why we're seeing so many dislocations. So based on our experience, we have seen that silicon carbide is pretty abundant in growth environments. And we can envision this as follows. If we compute the coefficient of thermal expansion of silicon carbide versus silicon. If you compute it and compare, we see that silicon carbide is much higher. That is, for a given temperature, silicon carbide will expand or shrink much faster. An animation in here will show that if you start cooling down from your annealing profile, the silicon carbide particle will shrink much faster, distort the lattice, and therefore create many dislocations such as we have seen in this work. So my two main contributions in this work is that, one, we identified the efficacy limitations for annealing, and this was in the form of second phase particles. And two, is that I presented a suite of characterization technique that can be implemented by crystal growers. So with this, crystal growers can now implement a more stringent environmental control to avoid having these particles within their sample. I now move on to the second part, or the next part of my PhD work, which is characterizing dislocations in multi-crystalline silicon. As I've shown, annealing dislocations can be troublesome, and it might not be the best route because it has limitations, as I've shown as second phase particle. The other route is to optimize the growth conditions, such that whenever you grow a wafer, the dislocation density is pretty low already. So I start first with multi-crystalline silicon. Why? Well, this material has the highest market share within the silicon breakdown. And something that is really interesting is that I told you how all dislocations are bad. But I lied a little bit because not all of them are really that bad. So here on the x-axis, you see dislocation density. That is the amount of dislocation you have per unit area or volume if you look at it to the bulk. And the y-axis, we see diffusion length, which correlates to lifetime, which correlates to efficiency. So you can see two different populations of dislocations. One with a low gamma and one with a high gamma. Gamma is what is called the recombination strength. That is how fast the carriers are recombining at a dislocation. So you can imagine that it's a high recombination, carriers or the electrons are dying off pretty quick. So that's a bad thing. And this can tell you, for example, which is the important thing, that for the same amount of defects, that is the same amount of dislocation that you can have two very different electrical impacts within the sample. When the crystal growers grow their samples, they cannot really assess what the type of gamma they have in their dislocations. So some dislocations might be good enough for the crystal growth parameter, some might be real detrimental. If they want to learn what is the impact of these dislocation clusters, well, they have to go through this very lengthy process to create a full solar cell, as I previously mentioned. Now, this is not only lengthy, but it can be costly. If we break this down, these three segments, into the cost component parts, we see that it's about a third of each one of them to create a full solar cell. Well, this part, to create a full solar cell, is about a third of the entire cost thus far. So it's lengthy, and it's also costly to produce a full solar cell. Now, that's not the end of the story. Once you get to here, you need to characterize. So there's electrical characterization and structural characterization. Electrical, you have a full solar cell, and you can apply different techniques, light beam-induced current or electron beam-induced current. So this, you can spatially resolve where the dislocations or where the defects are impacting your sample. But also structural in degree of complexity. You start with a microscope. You want to increase the resolution, then you have to increase also the type of equipment you have. That's more costly and more expensive. You want to increase the resolution to see through the sample and see the dislocation in the case? Well, you also need to increase the type of equipment. And for those of you who are experimentalists, you know how much of a pain it is to prepare samples just for SEM, never mind for TEM. So this also, the characterization process is so time consuming and it's very costly as well. So the question is, can we use some simple technique that can characterize dislocations and their electrical impact? Luckily, this question has been proposed already for another type of defect. I talked to you about, how dislocations and grain boundaries are produced during growth. Well, for grain boundaries, there have been studies. So if we take if we zoom in into this grain boundary, we will see that that boundary could be either very ordered, that is pattern, repeated, or if we take a look at here, you see it could be also very disordered, very random. So based on this interface properties, there have been some work that have related the degree of disorder at that interface to the recombination activity. And what they have shown is that high degree of disorder at the interface corresponds to high recombination activity. So high recombination activity, just to remind everyone, is bad. So high degree of disorder at the interface, that's bad. The hypothesis is then this order proxy has been established for grain boundary. Can we produce an analogous proxy that can counter the disorder or that can build upon the disorder of the dislocations just to assign the same recombination activity very easily? Well, to test this hypothesis, this is the variable of merit, surface geometry. What you see here is a population with dislocations that are ordered. On the right-hand side, a dislocation population that is disordered. You see here on the surface are circular edge pits, and they're all continuous. We inferred that the line dislocation is in this pattern as well. When we look at this disorder array on the surface, we are hypothesizing that the dislocation line is going as is shown here. If we take the top view of the dislocation, this is what you would see. A similar pattern all throughout in an order type of dislocation cluster, and one with degrees of shape variation on the disorder. If we take a cross-sectional view of what that might look like, you would see that this same edge pit as a cross-sectional view would be something as this, which is a dislocation line intersecting 90 degrees of the surface. But also in the disorder, you will see dislocations intersecting at different degrees. To quantify this, I propose the eccentricity method, which is a parametrization of the function for an ellipse. 0 is equals to a perfect circle, and 1 will be an elongated ellipse. And from here, we can quantify now the degree of disorder at the surface. We have surface, but now we want to correlate with the electrical activity. To do that, we start here. This is a multicrystalline silicon sample. It has been processed into a full solar cell. You see a quantum efficiency map, internal quantum efficiency map, which is related again to the diffusion length. We create some correlated microscopy. That is, we pair these two maps, and then from here we can extract dislocation density as a function of internal quantum efficiency. This is the same plot that I showed you before for different gaps. Now, in here, cluster A is the more benign, the less recombination active, or the lowest recombination strength. And as you start increasing or progress in alphabetical order, the recombination strength starts increasing. And so in this case, goes from cluster A to cluster E, 5 different dislocation edge clusters with 5 different recombination strengths. So we have these two variables now. I talked to you about how the electrical recombination can be correlated with metal impurity decoration. Well, to assess and corroborate that this was the fact in this case, we performed some micro X-ray fluorescence at the synchrotron. This was done at Argonne Photon Source, Argonne National Labs, the Advanced Photon Source in Chicago, Illinois. And from here we can do some elemental mapping and see the distribution of different elements present in our sample. I'm sorry, silicon. This was done with a 10 kilo electron volt energy and with a 200 nanometer spot size. So just so you can get an idea, this is so small that your fingernail grew that in just 3 minutes. That's more of a beam spot we use. We assessed 3 different dislocation edge clusters. The best, the one that is so-so, and the worst. And from here, low recombination strength, high recombination strength. And what you see is as follows. You see the dislocation edge pits on the upper part, and on the bottom part, you see that channel that corresponds to copper. So there is no copper matching the existence of dislocations. As you start increasing the recombination strength, you see that in fact, there is now the presence of some metal precipitates, that is copper precipitates in the vicinity of dislocation edges. As you increase the disorder, you increase the recombination strength, and you start seeing more and more of this precipitates surrounding the dislocation. So to correlate these two, we see that the surface, this is a schematic representation. Well, this is a representative region actually of the lowest recombination strength cluster. That's cluster A, and this is the worst cluster, the highest recombination strength, cluster E. From here, you see that dislocation edge pits are pretty patterned. The cluster E are disordered. So we can compute the following graph. X-axis, as you start increasing the recombination strength, which is bad, the degree of variation of the edge pit eccentricity is changing and is more disordered. So in other words, what you're seeing here is that higher eccentricity variation, higher disorder, corresponds to higher recombination strength. I talk about surface electrical, but the hypothesis, what we saw on the surface, is that really happening in the bulk. So what you see, this is the histograms from the edge peak variation that we saw on the surface, from best, that is tight distribution, that is order, to worst, spread distribution, disorder. We perform some transmission electron microscopy, that is to see through the bulk. And what you see is follows. This is the pattern dislocation edge peak cluster, cluster A, order, and we see in the bulk. One end of the line is the end of the dislocation at the bottom, and the other end of the line is the end of the dislocation at the top. So you're seeing through the dislocation through the bulk. You see dislocations in the bulk are also patterned and continuous. That is not so true with cluster E, which was the hydrogen combination strand. You see disorder on the surface, disorder quantified, and disorder inside the bulk. So there's a high degree of interaction within these defects. Now, this high degree of interaction can lead to high density of edge components of the dislocation, more kinks, more jogs, and thus reduce the nucleation energy barrier for precipitates. So the two main contributions, I propose an engineering proxy to successfully predict the relative recombination strength or recombination activity in multicrystalline silicon. And I applied this engineering approach based on a very scientific and rigorous suite of characterization techniques, which analyze not only the structure, but also the electrical properties of the sample. So this approach can enable crystal growers to substantially reduce the cost and the time to assess the material quality. As I was speaking, that thing became a thing of the past. The new thing now is high performance. Things are evolving so fast in this field that you need to catch up. So there's optimization happening here at the crystallization part. What exactly is high performance? Where people have fine-tuned the parameters during growth, and they have achieved a new type of sample, which is still ingot-based, but it has small grain size than traditional, and this, in turn, has a low dislocation cluster that appeared and disappeared through the entire height of the ingot. In comparison to traditional multicrystalline, dislocations tend to propagate through the entire height, but not so in high performance. Also, they have reported increased efficiency in this type of solar cell. There have been some reports actually that project that this material will constitute about 35% of the entire market share for crystalline silicon within the next 10 years. However, as you can see from here, there are still some dislocation clusters, and I happen to study them. So the first question is, okay, we see dislocation clusters. Are they still detrimental in this new famous material that is emerging? And the second question is, I developed this nice proxy for multicrystalline, traditional multicrystalline. Can I apply it in this new novel material? To address the first question, I first need to talk about phosphorus nutrition gathering. This is a process that is required to create a full solar cell, but it also happens to extract impurities out of the material. So PDG, phosphorus nutrition gathering, is for P-type, creates the PN junction, and what you see here is the three different stages. One, and here you can see the progression of the visual representation of a cross-sectional view from the wafer. This is a progression in time temperature from different stages. So you start cooling down your material, you end up with some dislocations, and you also have precipitated metals in the dislocation. You also have outside and dissolved metals within the vicinity. Now, phosphorus diffusion gathering, you start increasing the temperature. By means of increasing the temperature, you start to dissolve some of those precipitates. Now, those precipitates now become dissolved metals. It happens that phosphorus, you start depositing a layer on top of it as you are doing phosphorus diffusion gathering to create the PN junction. It also, for iron, it has a higher solubility in phosphorus than it has in silicon. So it's more energetically favorable for the iron, in this case, iron metal precipitates to dissolve and then to migrate towards the P layer on the top. So we're creating two effects. Now the optimization of this is the subject of PhD thesis, but in effect, you are extracting impurities out. To compare this versus traditional, to compare this effect in traditional versus high performance, I did as follows. You see here for multicrystalline silicon, as grown state, that is bare wafer grown, phosphorus gathered after you apply this process, dark is bad, white is good, this is lifetime. And what you see here is the ratio, that is before over after. Whatever is in red, that means it got degraded. So bad, it became worse. Red is worse in this case. We can see this differently. X-axis, as grown lifetime. Y-axis, phosphorus gathered lifetime. I'm showing you also 3 different slopes. That is the intensity of the improvement. 1 to 1 stays the same. Anything below, the material performed worse after this process. And so when we plot the data, we see as follows. You see the data spread within this range, and we start computing the median values for every 5-second intervals. You see that most of the data or the median values fall below the 1 to 1 line. This is consistent with this because it's plotting the same data. So most of the material became worse after this process. Let's compare that versus high performance. You see here, as grown, phosphorus getter, you see more white now, which is higher lifetime. When you compute the ratio in here, you see that there's less amount of red areas. So it reacted better to the phosphorus getting process. As grown lifetime, getter lifetime, different slopes. Plotting the data, you see that the spread is now shifted upwards. If we compute the median values, most of it falls above the 1 to 1. That is, most of it improved. So the first insight from here is that high performance, it does respond to phosphorus getting. But the real question is why and where? To answer this question, I bring again multicrystalline silicon. You see the ratio image, red is that, remember. Now I'm showing you iron interstitial now, metal impurities, those are detrimental. You can see that this high, which is the white color, matches very well with the red area, which is the one that's underperforming. If we try to pair this with the dislocation density, we see that this region, the red underperforming region, would match very well with high interstitial iron, also corresponds to dense dislocation clusters. Is that the same for high performance? Well, it happens to be. We see red regions corresponding to high amount of iron, and these red regions, as you can see here, match also well with dense dislocation clusters in this material. So underperforming regions after phosphorus gathering are corresponding to areas with high dislocation density clusters. And this is dense dislocation clusters. And this also corresponds well with the relative higher amount of metal impurities. Second question was, can we validate and apply this proxy that I developed of disorder to this new material? Well, in here you have a lifetime image. White, again, is good. Black is bad. So we select 2 different clusters that are shown here in this edge pit map, 2 different populations of dislocations. We zoom in, we now appreciate the degree of order visually in here and some disorder. But we need to quantify just to make sure. And in fact, the distribution of the order dislocation cluster is tighter than the distribution of the high recombination, which is the disorder one. So from here, we're validating the proxy developed from multicrystalline, extending it to high performance. And we see again that high disorder corresponds to high degree of recombination activity, and low disorder corresponds, or high order in this case, it's low recombination, which is good. Furthermore, we assess that this is in fact correlated to the presence of metal precipitates. Micro-XRF tells us so. This is a view of this disorder edge pits. In the vicinity, you see the presence of iron precipitates decorating those high recombination active clusters. 3 contributions. So from here, we elucidated the differences between traditional and high-performance multicrystalline silicon after the gathering process. We identified and attributed the underperforming regions that I showed to the presence of dense dislocation clusters. And finally, we extended the previously developed eccentricity proxy to assess the relative recombination activity also to high performance. With this, crystal growers can now shorten the feedback loop in this new material to keep increasing the crystal growth parameters. Something interesting happened when I was doing this work. It's not bad, by the way. I was observing the dislocation edge pit distribution, and it was as if they were trying to say something. So, as a matter of fact, the spatial distribution of edge pits have been barely studied, and there's some simplistic models that tend to point that the aggregation or agglomeration of dislocation edge pit tends to be worse. However, whenever we report dislocation density, we only report density, and that's it. And as you know by now, the same density can have very different impact. So if life is too short to be measuring eccentricity, then can we propose a spatial distribution metric that can tell us something about the relative recombination activity? Well, to test that, I went back to the sample that I had heavily and thoroughly characterized, which is this one, again, cluster A, cluster E, going from best to worst. You can see here the edge bit maps for different dislocation edge bits. I computed the center, that is the coordinates for where each edge bit was located. And this goes again from low to high recombination cell. From here, you can start seeing that there's difference in the spatial distribution of dislocations. I propose the use of the Morishita index. This is a spatial point pattern analysis that has been used to study the agglomeration of pine trees in Taiwan. So from here, we won't do that, but we will study though the spatial distribution of dislocation edges. So this is as follows. This index is a function of the number of quadrats, the number of points in the quadrats, and the number of total points. So the quadrat is the minimum frame distance that you would be using. That is, you create a mesh and take the unit distance within that mesh. What tells you, the Morishita index tells you, is as follows. Whenever you have a cluster pattern, you would have a value above 1. That is, the likelihood is high of having 2 points coming from the same quadrant. That would mean that there is a dislocation cluster. If the value is 1, may or may not be, it's a random distribution, a +1 distribution. And if it's below 1, that is that the likelihood of the 2 different points, in this case, edge bits coming from the same quadrant, is very low. In this case, they would correspond to a regular pattern spatial distribution, 1 randomly distributed, and above 1 cluster. Now this, as I mentioned, is a function of the quadrat size that you select. And the selection of the quadrat distance is based upon information that you know a priori from the phenomenon you're studying. So to determine what our quadrat of interest or a critical quadrat threshold would be, I selected cluster A, which is the best, and I saw that there was a pattern that I was already visually observing. So I measured the distance between dislocation rows and selected that distance to be my quadrat threshold. The results are as follows. You see here cluster A, which is the best, going all the way to high recombination strength, the worst cluster. But you also see something interesting. When you measure the Morishita index, you see that it goes from pattern, which is what we're seeing, we're observing its pattern, it's regular, it's below 1, and it evolved into a value of Morishita index above 1. So that is that this is agglomerate, it's clustered. So in this case, just computing the values of the index at the critical threshold that I established, we see that there's an evolution going from pattern to agglomerate. Again, low recombination in this case becomes pattern, high recombination, agglomerate. So there's 2 main contributions from this piece of work. 1, this could potentially be a new way of reporting dislocation density for experimentalists. We can now assess the distribution, but also how the density, well, pairing of the density and the distribution as a spatial proxy that can describe the relative recombination between different clusters. Further tests in an industrial scale would be required, but this has the potential to be a robust approach that could maybe, in turn, substitute the eccentricity proxy that I previously proposed. So, in conclusions for my PhD work, in low-cost materials, dislocations still limit performance. We need to reduce the number of highly recombination active clusters. And we can do that either by dislocation density reduction, that is high temperature annealing. But as I show you, that comes at a consequence because you will start nucleating more and more dislocations, so it has its limitations. The other route is to optimize the time temperature profiles and the growth conditions. And that can be done with the eccentricity and spatial proxies that can reduce cost and time. And with the advent of novel materials, high performance in this case, it would require further improvements, but with this proxy that I propose, they can be really helpful to reduce cost and time. So from here, crystal growers can characterize their materials in a rapid manner at low cost. So instead of using all these techniques, they can use only the optical microscope. And instead of going through the entire process to have a finalized cell, they can cut this area and end up only with a wafer that can be characterized. So I would like to thank so many people. I think I would require another 45 minutes. But I should start by thanking my family who are here second row. So they came all the way from Mexico to hear me talk today. I cannot stress how grateful I am for their presence and support all these years, for picking up the phone at weird hours just to hear me and advise me on things. So thanks to all of you, and some of you are here online watching, so thank you very much. And for those who are absent as well. I want to thank Pupi for your support all these years in the good and bad times, and for your love and comprehension as well. She even came down to the lab to help me out when the experiments were not going well. So she deserves a huge credit in whatever good work I showed. The bad thing is all me. The Dream Team committee members, I cannot stress how grateful I am for all the wisdom you imparted me during our committee meetings. So thank you so much. All my Martha friends, some of them are located here today. It was such a pleasure to be having so much fun as I was having inside the lab. So I was really excited about spending so much time with you guys. It's been such a pleasure. I'll let you take a picture. And so to also many other friends that I made along the way. I don't think I have enough pictures to show all of them, but here's just a representation of the pictures that I have. And for all the friendship and all the joyful moments that you gave me throughout my PhD, I thank you so much. I look forward to continue nurturing this relationship that we started here at MIT, which will be a lifelong relation, I hope. Also to the PD Lab. Last time I checked, it was ranked at #1 in the best research groups at MIT. I've been holding that position for 8 years, I believe. It's such an amazing people. I'm really impressed by how smart but funny and diverse team we have built, and that is thanks to Tonio's strategically choosing them. I think. And lastly but not least, of course, to the man, El Jefe, Tonio. Tonio has been, I cannot really put it to words that he's such a role model, a visionary, a great manager, a leader, and more importantly, he became a friend to me. So Tonio, thank you for taking the huge risk and gamble of accepting me in your group. I really hope it will eventually pay off.
Already have.
But it was because of all these people that I was able to grow as a scientist as well. So thanks to all of you who made me do some contributions to the scientific field and grow as a person. So this is some of the accolades that I was able to achieve, but it's all thanks to you and it's all yours. So with that, I will now leave the room open to any questions that you might have. Thank you.
So Sergio did a great job buttering you all up for questions. But it's our job to really query and test the examinees. So first step is to open the audience, so everybody but the committee. And then after that, Q&A, we'll ask the audience to leave, and the committee will interrogate Sergio. And then finally, the committee will deliberate. So first, questions from the audience.
Yeah. Sergio, you made a lot of great tools, and you're saying that it'll be very useful. But where do you see your tools being used? Do you see them being used in labs at companies? Do you see industry picking them up? Where, at what process? The research, the development?
Yeah, I hope it is at companies, because a lot of the research we do in the group is very grounded in scientific argument, but the whole goal is to help industry. So my goal is shared with the group, it's helping industry. So I do envision crystal growers, that is R&D labs, growing and manufacturing this breaks or this material. implementing this technique to rapidly assess the material.
So I'm just curious, but how much do you think implementing the things you suggest will bring down the cost of CRPP today?
How much, what, sorry, was it?
But how much do you think your proposal will bring down the cost of CRPP today?
Well, I've read that the best case scenario, if we get rid of this location, is about 40% relative efficiency that would get incremented. So that would be huge if that's the case.
How much did he pay you to stay silent?
What they promise.
You got my email, right?
Yeah.
So the tools that you're proposing, as I understand them, would allow an ingot grower to evaluate a methodology in their product line, and then have faster feedback loop. So what kinds of changes, does this inform in any way, or can you describe to us what kinds of changes they could make in that product line to reduce the dislocations and improve efficiency outside of the initial annealing process that you mentioned and has some limitations?
So most of the time, what they do is they fine tune the time temperature profile. So that's one of them. They can also fine tune whenever you deposit in the ingot, they apply some linens. They can change that. I've seen some recent articles that detail how that impacts the structural properties afterwards. So temperature variation, that is, I think, by far the most sensitive thing they can do. The environment is the second. The third one is the growth conditions of the initial feedstock. So right now, the high performance, it's already an evolution that led to fewer dislocation density. So you can think A to B, so B to C can be built upon the same ground, that is fine-tuning how the initial feedstock was placed. In this case, for high performance, what they do is they crush some chunks, and then they use that as a template to start building up new grades. So something along those lines, which is changing the initial state, would be something that could potentially be implemented. That's what comes to mind right now. I have not really dived into the crystal growers' expertise, but that's what I've learned. By the way, Kevin Cockey was my boss when I did an internship back in Arizona installing solar panels, and he happened to be in the area. So it's great to see you after all these years.
So Alex and Marcus.
So for a lot of these disordered phases or boundaries, you get this competition between a nice, perfectly ordered boundary that might be very enthalpically favorable often, sort of where it should be, competing with entropic drive to have some disorder. I don't know if that applies here, but is there sort of this competition between higher temperature where you might want to, or might be able to wheel out these dislocations, but also introduce a stronger entropic drive, and do you see any kind of disorder or transition based on temperature there with these dislocations?
If I understand correctly your question, you're asking if the high temperatures, if the temperatures have something to do with the degree of order that I observed. Is that correct? Yes.
Yeah.
Okay, so let me show you real quick. I'll go back to one slide. The TEM one.
These are coal train cars, as Sergio explained to me when he's trying to displace in West Virginia.
So I show you some TM of the order. What I show you here, which is what's not stated, is the plane traces. So these locations tend to glide along the 111 plane. However, when they recover, that is, they restore their mechanical properties, they tend to attain this low energy configuration. So we see that in fact, whenever we see order, is because they attain a low energy configuration, and that is a process that precedes crystallization. So it's like a cannibalization of the strain energy within the material that leads to this recovery. Now, this recovery occurs only at high temperatures, and so we hypothesize that in fact, whenever you see disorder, it's because this dislocation were created at really high temperatures. They have the time and temperature to arrange themselves in a low energy configuration. Whereas in here, as you can see, well, they align themselves in a plane perpendicular to the 111. So this is the 111 plane, and they are aligned perpendicular. If we do that same analysis on the high disorder, we don't see that happening at all. So they don't attain this low energy configuration. So we hypothesize that these are actually nuclear upon cooling. So they don't have that time nor the temperature enough to attain this low energy configuration. Yes.
You described the dislocations primarily indicating during the process of crystallizing the ingot, but I guess your analysis was largely performed on wafers that had been sawed, right? So does the sawing process introduce more stress and potentially more dislocations? And if so, how do you kind of deal with that?
Right. So let me show you real quick in this slide. So dislocation happened to nucleate at high temperatures. So anything below 500 to 600, you'll fracture the material. So sawing occurs at room temperature. Maybe the friction elevates the temperature locally, but you will not be able to create dislocations, at least not in the way that we see them, just cascading over and over. Was that clear?
Yeah.
Okay, great. And Maurice, yes.
Yeah, so you've developed a methodology for the reduction of these dislocations. You've shown you match for two types of material, the one that are standard multicrystalline and the high performance multicrystalline. What do you think, would this also hold for other types of multicrystalline material if you go to lower quality, for example? And second part of the question, can you imagine anything where this would break down, where this would not work anymore?
Since I understood your second question better, I'll start with that one. It would break down whenever you have really dense clusters. So in high performance, we observe really high, like dense clusters, but at that point, you cannot really compute the density to begin with. So those gamma plots that I show, the x-axis is the location density. So at that point, you really can't really tell where in the x-axis you are. So in that sense, you cannot determine the amount of dislocation, but also decoupling the shape of a dislocation edge bit is impossible. So that's by far the clearest point where this would break down. And the first one was the...
If you go to UMG or any material that is of much lower quality of the ones that are out there, would that still work?
I potentially see this happening, yes.
And what about the other way? How would this apply, or could it apply to single crystal products?
Well, single crystal, we're lucky enough that there's not enough dislocations in there. So I would, and let me go back to this gamma plot. I think it's pretty telling in the sense that, so whenever you have really low dislocation density, the impact that the dislocations have is pretty negligible. So for single crystal silicon, low dislocation density, I think it's definitely other defects that are dominating. So it shouldn't be a problem.
Okay. I think the audience, if you wouldn't mind standing outside, there's a nice milling area right here in the back.